we've had some exposure to special relativity. Let's take a look at a few more examples. And before we do, let's kind of lay down our ground rules: proper length and proper time. The proper length is measured by an observer for whom the endpoints of the length remain fixed in space. So if the length is in your rest frame, the full length, you have the proper length. And anybody else moving with respect to you is going to observe that length to be contracted. So the measured length of a body is greater in its rest frame than in any other frame. The proper time interval is measured by an observer for whom the key events take place at the same position in space. So if you've got a clock and the events that are key in this scenario take place in your reference frame where your clock is, then you have the proper time. And anybody else measuring those events, moving relative to you, is going to measure a longer time for those events. The time difference between the events represented by two readings of a given clock is less in the rest frame of the clock than in any other frame. Those are your rules. And looking at this, a useful formula is to be able to get the velocity quickly from gamma. So just reverse engineering the algebra of gamma, squaring it here, and then just a little bit of algebra. We have velocity squared is equal to 1 minus gamma to the negative 2 c squared, or our velocity, relative velocity, is equal to square root of 1 minus gamma to the negative 2 times c. For example, if gamma is 1.67, plug that in. 1 minus 1.67 to the negative 2 square root times c is 0.8 c. Nice to know. So kind of a little useful formula, especially for the problems. Muon decay. For muon decay, we consider Earth's frame of reference, but we did not consider the moving frame of reference, the muon's frame of reference. How rude. We should consider that frame of reference as well. The muon has a half-life of 2.2 microseconds, and from its frame of reference, that's a pretty short time. So, how is it that 75% of the muons actually survive the trip to the ground, to the Earth? Because for 2.2 microseconds, they should only survive for a certain distance, maybe 600 meters. Well, from their perspective, the Earth is actually rushing up towards them, and the distance between where they are and the Earth is a moving distance. It is going to be contracted. So from the muon point of view, the distance between the sky and the ground is contracted to a distance where their lifetime will allow them to make that contracted distance. How about that? So all is well. Relativity is truly relative. Suppose we had two meter sticks moving past each other along the direction of their length. We have meter stick A and B. If I'm riding in the rest frame of one of them and I measure the length of the other to be less than 1 meter, how can I conclude that my meter appears more than 1 meter long to an observer in the rest frame of the other stick? Good question. Each inertial frame must speak for itself. So what I observe is everything else to be contracted, and that will be what the other frame observes as well. Observations made in one frame provide a description of events only for that frame. Observer A sees B's meter stick as being contracted. Observer B sees A's meter stick as being contracted. And they both are correct. The only time we get into complications is if one of them decides to stop, turn around, and then try to compare notes. But if they continue on their merry way, then they can be assured that they are seeing it correct from their frame of reference. So two observers disagree on the time interval that takes place between two events in one of the reference frames and the distance between 2 points that remain fixed in one of the reference frames. So dealing with time dilation and length contraction, and whether two events occurring at different locations in both frames are simultaneous or not. So they'll disagree on simultaneity. So what can two observers agree on? Well, the relative speed of motion between the two frames. That speed of v is agreed to be the relative speed. And the speed c of any ray of light in either frame. All rays of light are traveling at the speed of light no matter which frame you're in all the time. So if we have a ray of light, we agree, both of us agree, that it is traveling at the speed of light. And we can agree on the simultaneity of two events which takes place at the same position and time in some frame. We can agree on that. Take a look at this. We have two spacecrafts. They're both the same kind of spacecraft, same length, and they're going to pass each other. And when these two dots coincide, spacecraft B is going to shoot a cannon from the rear end of the spacecraft towards A, and we're going to have a war, maybe. A Star Wars. But B doesn't see a problem with this because A's spacecraft is contracted according to B. And so when B shoots the cannon shot will miss, and it'll just be just a little warning, a love warning. So B's going to miss from their perspective. What about from A's perspective? When those 2 points coincide and B shoots the cannon, A sees B as being length contracted, and hence, from their perspective, it looks like the cannon shot is going to hit them broadside. Who is correct here? So we have these two scenarios. From A's perspective, they're going to get hit broadside. From B's perspective, the cannon shot's going to miss. Who's right? Well, we can only be sure in B's perspective the two events are simultaneous. The events that coincide with the dots and the shooting of the cannon are simultaneous events in B's reference frame. So, if we look at B's reference frame, we can assume those events to be true, and A's contracted, so the shot misses. What about A's reference frame? When those two dots coincide, the point at which the cannon is some distance away, and in fact, those events are not simultaneous in A's reference frame. In fact, the cannon is shot before those 2 points even coincide as far as A is concerned. The cannon is shot, the cannonball has gone by, those 2 points coincide, A is okay because the shot is already past the front of the spacecraft. So in either case, the cannon shot misses. The only one we can really be sure of in terms of simultaneity is from B's perspective. Pole and the barn paradox. A pole vaulter moving at 0.75 c, pretty fast, so it must be a Olympic pole vaulter, carries a horizontal pole 15 meters long toward a barn that is only 10 meters long. Initially, the barn's front door and rear doors are open. An observer on the ground can simultaneously close and open the two doors by remote control. When the runner and the pole are inside the barn, the ground observer closes and then opens both doors so that the runner and the pole are momentarily captured inside, and then proceed to exit the barn from the back door when the doors are open. Do both the runner and the ground observer agree that the runner makes it safely through the barn? Okay, so we have a barn, and you're in the rest frame of the ground. Barn is 10 meters long. The pole is going to be length contracted. So even the pole is 15 meters long. As you see it, because it's moving, it's going to be length contracted. So maybe it'll make it through the barn. To the ground observer, the pole is contracted. What is our gamma here? Gamma is 1 over the square root of 1 minus 0.75 squared, which is 1.51. So to the ground observer, the length of the pole is the proper length, 15, divided by gamma, 9.9 meters. So it's possible that the pole could fit inside the 10-meter long barn. So he or she has no problem with momentarily capturing the pole inside the barn, push the button to close the doors. As soon as the pole is contained within 10 meters, push the button, doors close, open, and the runner was momentarily contained within the barn. No problem. However, to the running observer, the barn is contracted. The proper length of the barn is 10 meters, but divide that by gamma, and to the runner's observer, the running observer, the length of the barn is 6.6 meters long. That's good. This is much shorter than the 15-meter long pole in his hands. Does he make it safely through the barn? So the barn's contracted, even a bigger problem. So what's going to happen? Is he going to get stuck? Good question. The closing of the two doors is measured to be simultaneous to the ground observer. The length between the ends of the barns are at rest with the ground observer. The two events can be simultaneous in their frame of reference. However, for the runner, the doors are at different positions and they do not close simultaneously. The rear door closes and then opens first before the front of the pole ever makes it there. And the front of the barn does not close until the rear of the pole has passed by. We can prove this mathematically, but we need more tools. And for that, we need the Lorentz transformation equations. The Lorentz transformation equations enable us to transform coordinates from a rest frame S to a moving frame S prime, where the movement is along the x direction. So we have the moving coordinate x prime is equal to gamma x minus relative velocity times time. Y and z are the same because there's no movement in those directions. And then we can transform from the rest frame to the time in the moving frame. T prime is equal to gamma t minus v relative velocity v over c squared times x. So if we know the rest coordinates x and time, we can get the moving coordinates x prime and t prime. And going the other way around, in transforming from the moving coordinate system S prime to the rest frame S, simply replace the v by negative v and interchange the prime and unprime coordinates. So if we had the moving coordinates, we can get x equal to gamma x prime minus v should be t prime, y prime is equal to y, z prime is equal to z, and then we have t is equal to gamma t prime plus v over c squared x prime. So all we did was interchange v with negative v and interchange the prime and prime coordinates and unprime coordinates. Most often we'd be likely to know the displacement between two events and the time interval between two events. So those formulas are even a little bit easier. The displacement in the moving frame is equal to gamma displacement in the rest frame minus relative velocity times time in the rest frame. And the time in the moving frame, time interval, is equal to gamma time interval in the rest frame minus v over c squared displacement in the rest frame. So we convert one to the other really easily. Going from rest frame to the prime frame, and again, if we go the other way, we interchange v with negative v and our prime and unprime coordinates going from the moving frame to the rest frame. These are very useful equations. Let's try it out on the PoleBarn paradox. The lesson here is not that the door closings are not simultaneous in both frames. Consider the pole entering the barn and set t equal to t prime equal to 0 and x equal to x prime equal to 0 to establish that point as being our beginning point for both coordinate systems. The prime coordinates refer to the moving frame and the unprime to the rest frame. Gamma is 1.51. So let's look at the barn frame of reference first. X and t are position and time. T equals 0 when the front of the pole enters. When the back of the pole enters, we have to go the full length of the pole, which in that reference frame is 9.9 meters, contracted, traveling at 0.75 c. The back of the pole will enter at 44.09 nanoseconds. The front of the pole will leave after the pole has traveled, the front of the pole has traveled the whole distance of the barn, 10 meters. 10 meters divided by 0.75 c, 44.44 nanoseconds. So if you close the two doors right at 44.09 nanoseconds, you can contain the pole within the barn. Backup pole will leave at 88.53 nanoseconds, but we have no problem. He or she can close the barn and barn door simultaneously and contain the pole within the barn. What about the pole frame of reference? Well, the front of the pole will enter at t equals 0, t prime equals 0. The front of the pole will leave when the pole has gone the full distance of the barn, which is contracted to be 6.6 meters long. That's going to be at 29.33 nanoseconds. Whoa. Back of the pole will enter when the pole has gone its full length, 15 meters, at 0.75 c velocity. That's going to be 66.66 nanoseconds. And the back of the pole will leave when it's gone the full distance of the barn after that, 96 nanoseconds. How does this correspond to the gate closings in this frame of reference? Good question. Well, the front gate closes in the rest frame at 44.09 nanoseconds. But where is this in the moving frame? We use the Lorentz transformation to figure this out, noting that our x is equal to 0, and we have that it should be dilated time, gamma, 1.51 times 44.09, 66.66 nanoseconds. So the back of the pole makes it through before the front of the gate closes. Great. But what about the front of the pole? The back gate closes at 44.09 nanoseconds because it's simultaneous in the rest frame. But for the pole frame, this is 10 meters further beyond, so we have to use the transformation. In the pole frame, this time is equal to gamma times that 44.09 seconds. But then we have 10 meters for x at 0.75 c for the velocity, 28.86 nanoseconds. In other words, the back gate of the barn will open and close before the front of the pole ever gets there. And hence, it opens and closes, the front of the pole can go through, back gate will close only after the back of the pole is through, the pole makes it through the barn. Let's try the Lorentz transformation for the twin paradox. For the moving twin, the events of takeoff and arrival of the distant star Sirius take place at the same coordinates. So your delta x prime is 0 for the main events. And going from this moving frame to the rest frame, we have our Lorentz conversion, transformation. Delta x prime is 0, so we simply have our time in the rest frame is equal to the gamma time in the moving frame. In other words, it is time dilated. For the change of coordinates in the rest frame, Since delta x prime is 0, we have gamma times v times delta t prime. Gamma times delta t prime, as we just saw, is delta t. So we have velocity times delta t, which is delta x. So this is what we expected. No problem there. What about going the other way around, from the rest frame to the moving frame? The takeoff and star arrival events have coordinates equal to the length. So v times delta t is delta x. Delta x minus delta x is 0. So our change in coordinates for the main events is 0 for the moving frame. We already knew that. Moving frame has the clock, and the events of takeoff and arrival at Sirius are happening right there. So that delta x prime is 0. What about our time? Well, we know that delta x is v times delta t. Factor out delta t. So we have gamma delta t 1 minus v squared over c squared, but that's just going to be 1 over gamma squared. So we have gamma times 1 over gamma squared, which is going to be delta t divided by gamma. It works. That is the time dilation in reverse, going from the moving to the rest frame. This is as expected as well. So everything is fine and dandy using the Lorentz transformation equations. That concludes this lecture in special relativity. We're going to go on to considering energy next.